Alright, so we introduced the topic of limiting and excess reactants. So we're now going to take a look at that and consider a chemical reaction when we're considering limiting reactants. So in order to determine limiting reactants, we need to consider the moles of each reactant and the moles of the product, right? If I use X amount of moles of hydrogen, how much product is that going to make me? Right? If I use X amount of the chloride, how much of that product am I going to make? So we can't simply determine. From the amount we have in the reactant to determine which one is going to be the limiting factor. Right? What we need to do is we need to just find out how many or how much of the product we can make. So here we convert moles of hydrogen. So we're just assuming, let's just say we have 3 moles of hydrogen and 2 moles of chloride. When we convert those into moles, what we need to do is we're going to use some stoichiometry. The stoichiometry we've learned in the reaction to determine how many moles of the product we can make. So whichever reactant makes the smallest amount of moles in the product, that's going to be our limiting reactant. Right? So here we can see if we had 3 moles of hydrogen, 2 moles of chloride, we're going to get 6 moles of hydrochloric acid, but here we get 4 moles of hydrochloric acid, and we can see that the chloride is going to produce less. So the hydrogen is excess, and the chloride is going to be our limiting reactant. So here we have another reaction. Which one is the limiting reactant? And we're given some amounts here in grams. So we have 2.00, I'm not a fan of black and white, so over grams of silicon. And we have 1.50 grams of nitrogen. Now, which one is going to be our limiting reactant? So the process here is, well, we can't compare grams to grams. We need to compare moles and moles, right? So first thing we need to do is get these into moles. Nitrogen is 14.01. Let's see what silicon is. 32. I have 28.09. Is that sulfur? Oh, that's sulfur. We need silicon. Si. Yeah, so 28.09. So this is 28.09 grams of silicon for every mole of silicon. And because there's 2 of them, we're going to have 28.02 grams of nitride for every mole of nitride. So here, these units go away. These units go away. And let's see how many moles of each one of these we have. And actually, we'll just go a little, let's see. Yeah, let's go ahead and, I was going to go a step further, but we'll stop here for a second. So here, how many moles of silicon are we going to have then? So you can all calculate that out. Calculators, bring your calculators for the next month. All right, we have more calculations next week. We're into gas laws, gases, tons of calculations, right? So bring your calculators out. We are going to be doing a lot of calculations. 0.0712. And then for nitrogen?
0.107.
0.107. All right.
What would be our sig figs for these?
Let's stick with 3 significant figures. So if we're starting with 3, then we'll end with 3 as well. All right. So now that we have the moles of these, well, how many moles of this, right? How many moles of the silicon nitride am I going to get from that if I use 2 grams of silicon? So we're going to use the stoichiometric factor. So what is the factor, the stoichiometric factor from 3 silicon and just simply 1 silicon nitride? So we say for every 3 moles of silicon, there's just 1 mole. 3, 4. So how much of the product am I going to get?
0.02.
0.037.
237.
And we're going to now compare the same thing. Using here, for every 2 moles, we're going to get 1 mole. So we use that stoichiometric factor, 2 moles. Right, these units here go away, these units here go away. So how many moles am I going to produce? So it seems here, even though we have more grams of silicon, that's actually our limiting factor, is that we're only going to be able to create or to make 0.02 moles of the product, right? So this happens to be our limiting reactant, that we have excess nitrogen gas. Let's do one more. What is the limiting reactant when 5 grams of hydrogen, 10 grams of oxygen react to form water? Does anybody need this here? Damien? Sure. Good. Notice that there is no reaction here for us, is that we have to write our own reaction. So when we take some water or some hydrogen, plus we're going to take some oxygen, we are going to get some water. Well, it seems there's 2 oxygens here. I only have 1 here, so I'm going to put a 2 here. I have 4 hydrogens here, which means that I'm going to put a 2 here, and now I have a balanced reaction. And now we can start. All right, so we have 5.00 grams of hydrogen, and we have 10.0 grams of oxygen. So step 1 is to convert these grams into moles. So H2, there's 2 of them, so this is 2.02 grams of hydrogen for every mole of hydrogen. And this is 2, this is going to be 32.00 grams of O2 for every mole of O2. All right, so here, is anybody confused where I got the 32 from? Does anybody need to know? We're good? All right. So I'm not going to put the equals here. So I'm going to continue here, because I'm going to convert grams of H2 into moles of water. So we're just going to continue. The stoichiometric factor here is for every 2 grams of hydrogen gas, we're going to get for every 2 moles of hydrogen gas, we're going to produce 2 moles of water. So here we're going to put 2 moles of hydrogen for every 2 moles of water. This unit cancels this unit cancels this unit. So whatever my answer is here is going to be in moles of water. And we're going to do the same thing down here. We're just going to continue. For every 1 mole of O2, we have 2 moles of water. This unit cancels this unit cancels this unit, so whatever I have is going to be moles of water. So 5 grams of hydrogen, how much water is that going to make? Or how many moles of water are we going to get from that? 2.47. So 2.47 moles. And how much with 10 grams of oxygen?
0.625.
0.625? So which one is our limiting reactant? Which one is made smaller?
Water.
Since this is smaller, this is our limiting reactant. So if we were to do this, theoretically, this is how much we're going to make. Right? Because it's the limiting reactant, we're only going to make 0.625 moles of water. Any question on that? No? We're good? All right. We've had a little experience. In the labs, we've had a little experience with theoretical yield, with actual yield, and determining the percent yield that we produce, right? So theoretical yield is here. This would be considered our theoretical yield, right? Is 0.625 moles. The actual yield comes from our experiment, right? Once we do the experiment, we're going to determine how much we get, and we compare that to the theoretical yield, multiply that by the 100, and we get our percent yield. So let's take a look and let's calculate our percent yield. So it says upon reaction, there's 1.274 grams of copper sulfate with excess zinc metal. 0.392 copper, so this is how much copper was obtained. So the 0.392 grams of copper, is that our actual yield or is that our theoretical yield? It is the actual yield. Is that it's telling us we did this reaction and we got our actual yield was 0.392 grams of copper. So let's determine what our theoretical yield should have been. We have 1.27 grams of copper, so 1.274 grams of copper. Copper, 63.55 grams per mole. I'm going to write it over here. So copper is 63.55 grams per mole. Is that right? Let me double check. 63.55. Okay. So, in order to determine this, right, we have to take some steps here. Oh, this is copper sulfate. Oh, big mistake here, Alex. This is copper sulfate. Does it say copper 2 sulfate or just says copper sulfate? Copper 2 sulfate. Oh, it is copper 2 sulfate. All right. So copper 2 sulfate. So this is copper. What is sulfur? So we're going to have to add all of this up here.
I don't see copper 2 sulfate.
So what's the charge on sulfate? Which means copper is 2+. So this is how we know that it's copper 2. sulfate. Simply divide by the anion that it's with. So what's the mass of sulfur?
32.07.
And what's the mass of oxygen? 16.
16.
So with oxygen, there's 4 times 16. So somebody add all this up. 63.55 plus 32.07 plus 4 times 16 here. Add all that up. 159.62 grams of copper sulfate for every mole of copper sulfate. All right. We're going to use stoichiometry that we learned the other day. And for every 1 mole of copper sulfate, there's 1 mole of copper. So for every 1 mole of copper sulfate, there's 1 mole of copper. So we can see our units begin to cancel out. And we've now converted these grams of copper sulfate simply into just grams of copper. So our last step here is we need the theoretical mass of this. Right. So here, we're going to use this over here. We have 63.55 grams of copper for every mole of copper. This goes away, this goes away. So what is this value here? Did we get anything, Amber?
0.507.
So 0.507?
Yes.
Yeah.
So 0.507 grams of copper. So matches our answer here, right? 0.507 grams of copper. So this is the theoretical yield. That's how much we should have gotten. So we're going to take our actual yield divided by the theoretical yield, and we're going to multiply that by 100. So let's multiply that by 100. And what is our percent yield?
$77.3.
So we had a 77.3% yield, right? So we lost about 20 some odd percent. So we lost about 23% of our product. So this is our comparison to percent yield. So let's do one more of these here. This time comparing. We do have excess hydrofluoric acid, as it notes here. What's the percent yield of the reaction that produces 12.5 grams of gas freon from 32.9 grams of carbon tetrachloride? All right. So we had, this is how much was the actual yield, 12.5. So we're going to calculate our theoretical yield. So our actual yield (12.5 grams) was our actual yield.
And we know it's the actual because it says that it's produced.
Yes,
Okay.
a reaction that produces this much. So what is the percent yield that produces from 32.9 grams? So we're going to start with 32.9 grams of carbon tetrafluoride. So step one, we have to convert this into moles. So we have carbon and chloride. Carbon is 12.01. Chloride is 35.45 times 4. So what is that molar mass? Said 152.81. We're good? 153.81? Do we match?
Yes.
All right, 153.81 grams of carbon tetrafluoride for every mole of it. I'm going to cancel these units out now. So we're at moles of carbon tetrachloride. We need to convert this into moles of this. And we see here, what's the ratio between those moles? It's a 1-to-1 ratio. For every 1 mole carbon tetrachloride, we have 1 mole of freon. Excess hydrofluoric acid. So this unit cancels out this unit, but we need the grams of this. And right now we're only in moles, so we get the grams from the molar mass from the periodic table. We have carbon, fluoride, carbon. It's going to be 2 times 35.45. This is 12.01. Fluorine, 18. We'll just say 19.00. So what is the mass of that?
I got 101.9.
101.9? Yes?
Yeah.
Okay. So 101.9 grams of freon for every mole of freon. This unit cancels this unit. So how many grams of freon are we going to have?
I think it's 120.
120?
Yeah.
Like this?
Yes.
We're good? 120? All right, so let's fix this. 120.9. 25.86 grams. So here, 25.86. So what is our theoretical yield for this? I'm sorry, our percent yield. That's our theoretical. What is our percent yield? $28? 48.34. So that is our percent yield. So we lost a little over a half of that in this reaction here, from actual to theoretical. All right, some more quantitative analysis. We've done titrations here. We've seen similar calculations here. I believe we did one in the actual lab, but we didn't fully understand what the titration was. But now that we know stoichiometry, right, we know how to use these reactions to get our stoichiometric ratio. We've gone from grams to moles, convert that to moles of something else, and then convert those into grams. With the titration, the step changes slightly. Because with the titration, we don't have grams of something. We have the volume of something. So we're going to need to learn how to convert volume of some reactant, some titrant, and convert that into the volume of some analyte, right? So remember that our titrant, this is our known concentration. This is what we have in our burette. We put the titrant into the burette, and then the analyte is the unknown solution that we're trying to neutralize in that acid-base titration. We use indicators in order to let us know this, right? The equivalence point here, and at the equivalence point, this is where the solution is then neutralized, and we can stop the titration, and we can then use the stoichiometric ratio in our reactions. So here, let's start with this one here. So the end point in titration, the end point in a titration of a 50 milliliter sample. For titrations, you're given a lot of actual information that we need to keep separate. We're given, this is our 50 milliliter sample of hydrochloric acid. So this is how much, if we're doing our titration, right, 50 mils of hydrochloric acid. The end point was reached. So here, in here, is where we have the 0.250 molar sodium hydroxide. And in order to reach the end point here, to where it was neutralized, is we had to use 35.23 milliliters. So 35.23 milliliters of sodium hydroxide was used in order to titrate 50 milliliters of that hydrochloric acid. So what we have to do, well, we have to now determine what this concentration is. So here we have this reaction here. So the process for this is that we take the volume of sodium hydroxide that we use. This is from the burette. We use 35.23 milliliters of this. We convert these into, because if we're looking at concentration, in order to determine concentration, what we're trying to determine, this here is in moles per liter. So this is in moles per liter. These units are in milliliters. So it's obvious that we need to just convert those into liters. So that would be it. This is our step here. Right? We convert milliliters to liters, and then we use this concentration, use the molar concentration to determine the number of moles of sodium hydroxide. Next step, we're going to use the stoichiometric factor in order to determine the number of moles of hydrochloric acid. So here we have 8.81 times 10 to the minus 3 moles of hydrochloric acid. But how do we get the concentration from this? Moles over liters. What liters? The 50 milliliters. So we're going to do a conversion of this 50 milliliters. We have the moles of hydrochloric acid over the 50 milliliters. We're going to do this conversion, and we end up with some concentration here. All right. So now we're going to run through another titration. Right? We're not going to use the flow chart. We're going to walk ourselves through this to determine what that other new concentration is going to be. And notice the difference here. Right? Everything here is in a 1-to-1-to-1 ratio. Right? We use the stoichiometric factor here, 1-to-1 ratio. But in this next problem, we are not at a 1-to-1-to-1 ratio. Right? So we're just going to write some information down here. We have 20 milliliters of our acid, oxalic acid. So here's our oxalic acid. We're going to titrate that with 0.09113 molar potassium permanganate. The volume of this that we used was 23.24 milliliters. So we use 23.24 milliliters of this here. Now, before we start, I think we should get rid of this M first, right? What we need is this. So I'm just going to write this over real quick. We're going to take 0.09113 moles of potassium permanganate per liter. Now let's start with our volume here. Our volume is 23.24 milliliters. All right. Our first step from the flow chart said that we're going to convert this into simply just some liters. So for every 1,000 milliliters, we have 1 liter. This unit cancels out this unit. Now, before we can convert moles of permanganate into moles of oxalic acid, we need to convert this to simply just moles first. And we have these liters down here. So we're going to go 0.09113 moles of potassium permanganate for every liter. And those units are canceled out. And now we have moles of permanganate. We need to convert moles of permanganate into moles of oxalic acid using our stoichiometric factor. So if we use that stoichiometric factor in this reaction, moles of permanganate into moles of oxalic acid. Well, what is the ratio between moles of permanganate? How many moles of permanganate? It's going to be the MnO4. And how many moles of oxalic acid? 5. We're going to continue because this is what we're looking for. We're looking for moles of oxalic acid per liter, right? We're looking for the molarity of this. And right now we just have the moles of it. We don't have any liters of it. We know that volume is in the bottom. So we're going to use 23.24. So 23.24 milliliters. And we're going to do one last conversion here. For 1,000 milliliters, we have 1 liter. This unit goes away. This unit goes away. Moles per liter. One last thing, is there anything else to make our calculation easier that we can cancel out here?
22.24.
The 1,000, right? This cancels this. So that makes our calculation just a little bit easier. So here, what is our final calculation here?
So what about the 20 millimeter?
Oh, did I use, oh. 24, oh, it should, this here. This should not be 20, this should be, I used the wrong amount, 20 milliliters. Thank you for catching that, John. So that does not get canceled out. Now for everybody online that's watching this, I have to write 20 milliliters, that goes here, not the 23.24. So what ends up being the concentration of our unknown acid, oxalic acid here? Let me calculate along with you so I can verify this one. 24 times 0.09113 times 5 divided by 2 divided by 20. All right, did we get an answer
We
to,
got 0.264.
or, yeah, 0.2647. So this is equal to 0.2647 molar oxalic acid. So there we go there. Oh, I wish we'll probably finish the lecture a little bit early. I think we're getting to the last portion of this here. Not too many more calculations. All right. So now using some stoichiometry to determine mass percent of some mixture, right? What is the percent of this in a 0.4500 gram sample, right? We can still use stoichiometry for this. Actually, any questions on titration before we move on? Where any value goes, comes from? We're good? All right. All right, so what is the percent mass for this reaction? So let's take a look at our flow chart over here. So we want to know the percent of this in a solid mixture that contains magnesium sulfate. Right? So what is that percentage there? So if we follow the flow chart, right, we're going to start with this mass that was provided for us. They provide us this mass. Let me double check here. They've provided us with 0.6168 grams. So I'm just going to write some of these here so I don't have to flip back and forth. 0.6168 grams of barium sulfate, and then we have 0.4550 is our sample mixture. All right. So we take the mass of the barium sulfate, right? We use the molar mass of it from the periodic table, and we convert that into moles of magnesium sulfate. This is the percentage that we're trying to get. We want to know how much of this is in that sample. We know how much the sample weighs, and we now have found out how much magnesium sulfate is in that sample. So this is a 1-to-1 ratio. This here comes from the reaction. All right. So that comes from our reaction, and we can see it here. How many moles, how many grams of this, right? So our mole to mole ratio, 1 mole of this for every 1 mole of this. And that's where that stoichiometric factor comes in down here. For every 1 mole of barium sulfate, right, we needed 1 mole of magnesium sulfate for that. Then we use our molar mass, and we have our mass of magnesium sulfate. We know what the mass of the sample is. We know what the mass of magnesium is. And we're able to calculate that that sample, this sample here, is 69% of this sample is magnesium sulfate. So now let's practice with another example here. What percent of this sample? So 1.1324 grams of the sample. So the mass of the sample is 1.1324 grams. And it produced 1.0881 grams, 1.0881 grams of silver chloride. What is the percent of chloride in this solution? All right. So here, the molar ratio between the chloride and the silver chloride is a 1-to-1 ratio. We're going to convert this into moles first. I can't convert this into chloride until we convert this into moles. Then we use our stoichiometric factor, moles to moles. So here, silver chloride. Gianni, do you have the mass of silver?
Yeah. It's 107.87.
So we're going to add these two up here. There's 2, 3, 3, 4, 1. So 143.32. So 143.32 grams of silver chloride for every mole of silver chloride. This unit cancels this unit. And now we can convert moles of this into moles of chloride. So for every 1 mole of silver chloride, we get 1 mole of simply just chloride ions there. Those units go away. But we can't, you know, this is grams. We have to convert this to grams before we can determine what that is. So chloride, this is going to be 35.45 grams of chloride for every mole of chloride. So how many grams of chloride did this consume in order to make it?
.267.
0.267 grams of chloride. Right? So then, right, the mass of this over the mass of this sample. So 0.267 grams over 1.1324 grams, multiply that by 100, and that equals the percent of chloride ions that we have. Yeah, sounds reasonable. So we got 23.6. We're good? All right. So, yes.
Isn't the sample, is that not the actual?
this is the mass of the sample. So here we're not doing percent yield, right? So percent yield, is that this would be our actual, right? So we're doing mass percent. So our mass percent, to figure out the percent, is the mass of the magnesium, or not the magnesium, so the mass of the chloride over the mass of the sample. So just slightly different, so we're not calculating yield for this one here. All right. Combustion. So combustion reactions, right? We're using carbon hydrocarbons. When we're using hydrocarbons, the products are always going to be the same. It doesn't matter what hydrocarbon we use, the results are always going to be the same. Is that anytime we combust some hydrocarbon, is that we produce carbon dioxide and water. I'll put up a sample, so let's see, we have in your car, if you don't drive an electric car, right, most of us are putting octane. This is octane gas. We put octane gas into our engines. Everybody here has an air filter in their car, right? We put oxygen into the engine. And what comes out of our tailpipes is carbon dioxide, plus on a cold day, you can see that water, right? I think my wife panicked one time. She saw water coming out of the exhaust. Oh, what's going on? It was just a cold day, right? But this is what's produced out of that combustion reaction. So it doesn't matter what the hydrocarbon is, right? We always have excess oxygen because naturally it's just in the air for a combustion reaction. The only time we don't have excess oxygen. Right? You ever seen those YouTube videos where if somebody maybe have done it yourself, you cover up a candle with a jar or whatever, and then all of a sudden stops burning? Well, that's because there's no more oxygen. Right? Combustion reaction requires oxygen, and if we remove this, but unless it's not sealed, right, is combustion reactions always have some excess oxygen use. But using this combustion reaction here, knowing that these are always going to be the products, is we can determine what the actual hydrocarbon is. When we look at these products here, if I write a stoichiometric ratio, I can say this one's not balanced. Let me write one that's balanced here. So let's do a simple one. CH4 plus O2, we're going to get CO2 plus, we're going to get some H2O. I do have to balance this real quick. 1 carbon, 4 hydrogens, 2. So this gives me 4 here, 2, 4. I'm going to put a 2. Okay, so this is now balanced. All right. If I use this and write a stoichiometric ratio, I can say that for every 1 mole of methane, we get 1 mole of CO2. Does everybody see where I got these from? And I'll write another one. We'll say for every 2 moles of oxygen, we're going to produce 2 moles of water. Everybody see where I got this from? We're good? Well, we can go a step further here. If we take a look at CO2, here, if I have 1 mole of carbon, how many moles of oxygen do I have? 2. I have 2 moles of oxygen. if I have 1 mole of carbon, we have, oh, again, 2 moles of oxygen. If I have 1 mole of oxygen, I have 2 moles of hydrogen. So everybody can see that, right? We're good with that. Okay. So we're going to take another one further step here. Right? Is if we're taking a look at water here. Let me erase most of this so that it doesn't get us any more confused here. There's a lot of arrows being drawn. Is that in water, so for every 1 mole of water, how many moles of hydrogen do I have? 2 moles of hydrogen. For every 1 mole of water, how many moles of oxygen do I have? 1 mole of oxygen. Right? So we can use this, right? So this can be converted into 2 stoichiometric ratios. We can say for every mole of water, we have 2 moles of hydrogen. Or I can write it for every 2 moles of hydrogen, there's 1 mole of water. And then depending on my problem, I can decide which one that I need, right? But they all come from this definition. So with this combustion reaction here, do they write us, what do they give us here? Let me write some of this information down. Because we're going to calculate the empirical formula of this. So we have 0.00394 grams of carbon dioxide. There is a 0.00126 gram sample of polyethylene. And we're going to get 0.00161 grams of water. So here, we're going to convert these grams here, right? We're going to convert grams of CO2 into moles of carbon. So this ends up yielding 8.95 times 10 to the minus 5 moles of carbon. Right? We use the molar mass. In carbon dioxide, for every 1 mole of carbon, there's 2 moles. I'm sorry, for every 1 mole of carbon, there's 1 mole of CO2. And we've converted this into moles of carbon. We take our grams of water. We use the molar mass, the stoichiometric ratio of hydrogens, moles of hydrogens and moles of water, and we convert that into moles of hydrogen. So we got 1.79 times 10 to the minus 4 moles of hydrogen. Now, we've done this before to figure out these empirical formulas. Which one of these is smaller? The 10 to the minus 5. So if I take this and divide it by this, that comes out to, did they do it here? No, they didn't do it here. We'll go 8.95 times 10 to the minus 5 divided by 8.95 times 10 to the minus 5. And this is equal to 1. For hydrogen, I'll put hydrogen over here. Oh no, they have hydrogen over here. If I take this and I divide it by the same thing, 8.95 times 10 to the minus 5, that comes out to 2. Right? So our our formula here, our empirical formula for polyethylene is CH2. All right, so let's try one more sample here. The steps are going to be the same. The steps will be the same. We're going to change the masses. Produce, so carbon dioxide, 0.00726 grams of CO2, and we have 0.00148 grams of water. So for water is 18.02 grams per mole, grams of water for every mole of water. And we don't need the reaction for this, we just need to know for every mole of water, how many moles of hydrogen? We don't have to reconvert this back into grams. We want the moles of hydrogen. We'll work on this one over here. So we have 12.01. Oxygen is going to be 32. 44.01. 44.01 grams of CO2 for every mole of CO2. The stoichiometric factor between carbon and carbon dioxide. For every mole of carbon dioxide, there's 1 mole of carbon. All right. So how many moles of carbon do we have? So we're looking for the empirical formula for polystyrene. Raga, do we have an answer? This divided by this, what is it?
I got 1.65.
All right, so let's, 1 point what? 1 point?
1.65 to the power of -4.
So 1.65?
Yes, 65 to the power of -4.
All right. So down here, how much hydrogen do we have?
We have.
No, we'll have somebody else calculate this one.
All this one?
Yeah, this one down here.
1.64 times
10 to the
-4.
-4, right? So do these values, are we good with these values? I haven't done the calculations, you tell me. So just verify that these answers look good. Both of them? We're
Yeah,
good?
yeah,
All right.
both of them.
What was that?
Yeah.
Both of them, all right. So since these are about the same, right? We can say this is 1.64 times 10 to the -4, and that equals 1.
1.
Divide this by 1.64 times 10 to the -4, and what does that equal?
1.006.
So 1 point, and round that,
0.1 to 1.
so 1 to 1. So we have a 1 to 1 ratio. For polystyrene, 0.00726, to make sure, 00726.0, oh, no, 00148. No, I used the right, okay, I'm just making sure I use the right values. 18, 44, 1, 2, yeah, no, these are it, all right. All right. Any questions on that?